These
most
quadrupeds
mammals use for
demonstrate
limbs to remain stable.
species-appropriate gaits. The synchronized footfalls highlight the mechanics of weight distribution.
Yet humans followed a different path. We stood upright. This change freed our hands, reshaped our bodies, and transformed our future. Walking onto legs now feels completely natural. Yet every step requires extraordinary balance and coordination. Our spine curves, our pelvis supports us, and our feet absorb repeated impacts. But this remarkable ability comes with serious costs. It contributes to back pain, damaged joints, and difficult childbirth. So why did our ancestors leave the security of four-limbed movement? Did standing help them travel farther, carry food, or survive changing environments? The answer begins millions of years before modern humans appeared. Our distant ancestors lived partly in trees. Their arms helped them climb and reach. Their feet could grip branches. Moving on for limbs provided dependable support. They were different. They belonged to their own evolving populations. Around 6 to 7 million years ago, human and chimpanzee lineages diverged. Early members of that lineage gradually developed traits linked with upright movement. It happened slowly. No ape suddenly decided to stand. Small anatomical differences accumulated across countless generations. Useful traits improved reproductive success. Their descendants inherited variations, supporting more efficient, upright movement. But the earliest stages remain incomplete. Fossils are rare and often fragmented. Bones and footprints reveal ancient movement. This evidence reveals a complicated transition. There was no single missing link. Many forms emerged. Some could walk upright while remaining excellent climbers. Others became increasingly specialized for life on the ground. Australopithecus lived about 4.4 million years ago. It had a grasping big toe. Yet its pelvis suggests some upright movement. This unusual combination challenges a simple story. Bipedalism may have developed within wooded landscapes.
Grasping hallux. Cautious, partially upright posture.
Later Australopithecines walked upright more regularly. Their arms and curved fingers still supported climbing. Their bodies were mosaics. They combined ancient climbing features with newer walking adaptations. The famous fossil Lucy belonged to this broad group. She lived more than 3 million years ago. Her short, wide pelvis helped support upright walking. Her angled thigh bones positioned her knees beneath her body. This alignment improved balance during each step. Then footprints provided even more vivid evidence. Ancient individuals crossed litholes with volcanic ash. Their footprints hardened and survived for roughly 3.66 million years. They show upright walkers with surprisingly human-like steps. Upright walkers persisted. Why did this movement become so important? Scientists have proposed several explanations. No single explanation solves everything. Different advantages probably mattered under different conditions. The changing environment offers one important clue. Ancient Africa never became endless grassland. Its landscapes formed shifting environmental mosaics. Our ancestors needed flexible ways to move between scattered resources. Standing could help them scan above vegetation. A higher viewpoint revealed food, companions, and possible danger. But looking over grass was probably only one benefit. Upright walking may also have saved energy. Chimpanzees can walk onto legs. However, their bodies make prolonged, bipedal walking relatively inefficient. Walking became efficient. Our body rises and falls like an inverted pendulum. Momentum carries us forward, muscles then guide and stabilize that movement. Human walking generally uses less energy. That difference matters when food and water lie far apart.
Ancestor
Efficient
A1,
travel could
general
expand
early
the territory
bipedal forager.
available for gathering.
Upright alignment.
Efficient foraging anatomy.
It could also reduce daily energy demands. Carrying offered another advantage. 2 free hands could transport food to safer locations. Parents could carry infants while moving. Individuals could bring resources back to companions. Sharing food may have strengthened cooperation within groups. Yet carrying alone cannot explain the entire transition. Early bipedal traits appeared before sophisticated stone tools. So tool-making did not initially create two-legged walking. Instead, upright movement later made tool use more convenient. Free hands could hold shape, throw, and transport objects. Feeding behavior may have contributed to. Primates sometimes stand to reach fruit or pull branches. Standing free both hands for gathering. Repeated feeding postures might have favored better balance onto legs. Heat provides another intriguing possibility. Upright bodies expose less surface directly to overhead sunlight. They also lift more skin into moving air. Sweating may have improved cooling. Further, cooler bodies could travel longer during hot periods. Still, thermoregulation was probably one piece of a larger puzzle. Display and communication may also have mattered. Standing makes an individual appear taller. It also frees the arms for gestures, threats, and social signals. Natural selection rarely follows one simple reason. Advantages accumulated as walking became common. The entire skeleton changed. Begin with the skull. One skull opening connects with the spine. This opening is called the foramen magnum. In humans, it sits relatively far beneath the skull. That position balances the head above an upright spine. A chimpanzee carries its head farther forward. Our spine also develops several curves. These curves place the upper body above the hips. They also soften repeated impacts during walking. But these bends create vulnerable areas. Discs can compress, muscles can strain, and nerves can become irritated. The pelvis changed even more dramatically. It became shorter and broader than an ape's pelvis. This basin supports abdominal organs during upright movement. It anchors muscle, stabilizing the torso. Those muscles work whenever one foot leaves the ground. Try taking a step for a moment. One leg supports nearly everything. Hip muscles keep your pelvis level. Without them, your unsupported side would drop. The thigh bones angle inward toward the knees. This brings each foot beneath the body center. Consequently, humans avoid swaying excessively from side to side. Our knees can straighten beneath the body. Their enlarged joints handle forces produced by every landing. But years of pressure can wear cartilage down. The feet underwent another major transformation. Our big toe moved into line with the others. It lost much of its branch gripping ability. Instead, it became a strong lever for pushing forward. Foot arches store energy and absorb shock. A stiff midfoot creates a stable platform. Thick heel pads cushion each landing. Shorter toes reduce stress during long walks and runs. Feet transformed completely. Our legs became longer too. Longer legs cover more distance with each step. Shorter arms no longer needed to support routine ground movement. The shoulders and hands gained greater freedom. Eventually, this freedom supported increasingly precise tool making and throwing. Upright movement also influenced endurance. Humans are not the fastest runners. Many four-legged animals easily outrun us. But humans can travel steadily for long periods. Several adaptations support our endurance movement. Our large buttock muscles stabilize the trunk while running. A strong Achilles tendon returns energy with each stride. The neck helps keep the head steady. These features became especially developed in later Homo species. By then, ground travel shaped daily survival. However, evolution creates compromises, not perfect designs. The same spine supporting upright posture often develops pain. Feet can suffer bunions, fallen arches, and damaged joints. Knees endure repeated loads far above body weight. Our pelvic floor must support organs against gravity. Childbirth presents an especially difficult compromise. An upright body requires a pelvis suited for stable walking. Meanwhile, human babies have relatively large heads and broad shoulders. The birth canal must balance these competing demands. Its twisting path makes human birth unusually challenging. Yet walking efficiency does not depend on one perfect pelvic shape. Human bodies vary, and childbirth involves many biological factors. Babies also need time to master upright movement. They first strengthen their necks, trunks, hips, and legs. Crawling helps develop coordination. Standing then demands balance, confidence, and constant sensory correction. Every toddler repeats the evolutionary challenge in a personal way. Fall, rise, repeat. Other animals also use two legs. Birds walk bipedally, while kangaroos hop using powerful hind limbs. But humans habitually stand and walk with a uniquely adapted skeletal system. Our upright gait did not result from one sudden invention. It emerged through many adaptations, environments, and evolutionary compromises. Every ordinary step carries evidence of that ancient transformation. Walking on two legs did more than change our movement. It changed humanity.